Hi everyone, I'm Xiaohua Xu from UT Austin. Sorry that I had to make this lecture in this format. So we'll be going over the tools in GMT to plot geodetic data, mainly targeting plotting vectors. So there are like many kinds of geodetic data, like grids or lines or vectors or like deformation field. And GMT has all the functions to plot them. But over here, we're going to go over some of the functions, mainly using the plot function in GMT and with this -SE option for vector attributes. So there are like a bunch of commands that you guys can go through probably. And we're going to do this hands-on mode. So let me stop share and switch to the VSC. Share screen. All right. So over here, what we're going to do is that we'll do a real demo to sort of go through all these vector attributes and sort of help you guys understand how you can control the plotting vectors. So let's get started. We're going to do a GMT -- new script. We're going to do it in bash. So let's call this plot vec dot sh. And now you see that, oh, I'm in the wrong directory. Let me move this to this directory, go to vectors. So there are like a bunch of files in this folder that's downloaded before this part starts. So that contains some of the example data sets that we're going to use later on. But for the moment, let's open this plotVec.sh. So now you can see that this is calling bash, and you want to specify a session name, just call it 11. And we want to call this figure name to be vec, and in the format of PNG. But before we really get started, we do want some data to be plotted, right? So we're going to create a data using the echo command. Say that we want to plot a vector that starts from 0, 0, with the value being 1 and 1. Because this is using the -SE option, so it's actually allowing you to plot the uncertainty circle. So we're going to add some uncertainty to this arrow, that is 0.2, 0.2. And the last column in the input is actually the, the correlation between these errors. For the moment, let's just call it, we're going to use no correlation between them. So in the end, it's going to come out as a circle. If you give it some kind of a correlation, then it's going to become an ellipse. So let's pipe this data, redirect this data into a file called maybe temp.dat. And then we'll start plotting. So the command that we'll be using in GMT is called willow or PS willow. And using the -SE option. So there are 3 inputs associated with this -SE option. The first one is the scale you'll be plotting. So here we're going to just use full scale, like 100%, which is 1.0. And the second input is actually the confidence level. So here we're going to use 6.65, which corresponds to like 1 sigma. So that's basically when you give this number over here, if you use 1 uncertainty, it's going to show up as the exact value. And the last one is actually the font size. If there are any like label associated, we're just going to use default like 10 over here. And we also want to specify the some line parameters. We want to give the width of 1 pixel. And if we save this script, and then in the command window, let's call bash plot wec.sh. Oops, some error. South is outside of the 1990 degree. What's going on? Oh, because I didn't give it a projection. I forgot to give it a projection. So let's set a parameter called, let's say, JRB equals. Once J, let's use Cartesian coordinates. Say we're gonna give it a size of 3 and 3 because you know, this is sort of wraps up this vector. And minus R, let's start from -1 to 2, which matches the 3 sides. So everything is in scale, -1 and 2. And we're gonna give the frame annotation being 1, frame being 1, and G being 1, grid line being 1. And we're gonna call that parameter right over here. Let's call it $JRB. If we save it, let's go one more time. Okay, it has shown up. 1 second. Let me open this. Okay, make it a double column, close this. So now you see an arrow that starts from 0 to 1 with an uncertainty circle being about 0.2. So if we play with this uncertainty level, say, for example, that we want like 2 sigma, which corresponds to 95, you see this circle getting doubled. If we save this script again and then run the same thing, you see that this is getting twice of the size. If you want 3 sigma, which is 99%, you can do it again. See, it's getting like tripled. So the next one we're going to play with is the correlation between them. For example, we want this to have some correlation between these uncertainties. If we give it a number, for example, 0.5, that means these 2 errors are kind of associated with each other. The increase with one may or may not necessarily result in the increase of the other one. And if you run this script again, you see that, oh, the uncertainty circle becomes an eclipse that sort of represents more realistic errors. And close this. Next, we will be playing with this arrow over here. For example, if we want to change the size of it, we're going to use the -A option to control it. For example, we want to give it 20 pixel and with the +E, which means at the end, and the A, which is a fancy arrow. And if we save this and run this one more time, oh, you see that the arrow is becoming larger than before. Actually, there are more that you can play with. For example, we want at the beginning to be an arrow tail, then you just plus BI. You see now there's a tail over there. Yeah, 20 pixel might be too big. Let's change it back to 10. And for example, I want the arrow to be filled with, for example, blue color. Then you give it a +G, blue. If you save this and run it one more time, you see that it's the arrow and the tail are being filled with the blue color. And also the -W is actually controlling the line plot over here. But for example, if I don't want the arrow to be very thick, you can actually re-specify the width of that using the +P, which is giving it a pin, similar as the -W option, but for the arrow plot, let's give it a 0.1 pixel. And if we run it one more time, you'll see that the outline of these arrows are becoming thinner than before. And there's another option that allows you to plot only, for example, half of this arrow, which is plus L plus R. If you give it plus L, save it and run the script, and you see that only half of it is getting plotted. There's another thing that you can play with. For example, if you want to plot a right lateral symbol, what you can do is, for example, we don't want to plot any uncertainty associated with it. So we're just going to put 0 over here. And you run this. Oh, we don't want the tail either. Let's remove the plus BI. You run it. And then this is half of the right lateral motion, right? And you can basically duplicate this line. And we want to plot the right-hand side. But we want it to be shifted a little bit so that the two arrows are not at the same place. So we're going to use the -y shift option. Let's move it by maybe 0.2. But also to realize is that you don't want the arrow to be on the same side. So instead of EA, you want to BA. And if you do the script again, oops, I shouldn't have specified this twice. Let's remove the $JBR and run this one more time. Okay, now you have a right lateral motion symbol. So that's pretty much for the vector attributes. Next, we're going to go through another example that's associated with the Ridgecrest, the 2019 Ridgecrest earthquakes. So let's start a new script. Let's call it GMT minus new script equals dash into plot map.sh. Let's open that right here. And we don't need this anymore. So let's call this, do the same thing here. We want to call it a figure name. Let's say it's called demo. And it's also going to be PNG. But before we really get started to plot this map, let's go through some of the files over here. So what's originally in the tarball is actually these a couple of script. These a couple of files. We can actually do a ls-l ht, and you should be able to see everything in that directory. So this dm.cpt is just a color table for plotting topography. And this GPS data are actually acquired, the acquired coseismic deformation in it for the Ridgecrest earthquakes. If you do head GPS.dat, it's going to show you the top a few lines in it. You see it's composed of longitude, latitude, and east-north deformation. They are in millimeters. And also the associated uncertainty and their correlation. I mean, the last three columns are just made up, so they don't really mean anything over here. And this dm.dsam.grd is just a DM data over the region. You could essentially use the DM directly from the Hawaii website. But this one is a little bit different. This is the DM above the ellipsoid. I guess the one distributed at Hawaii is above geoid. There are some differences between them, but you could use either of them. This new faults.gmt are actually the mapped rupture and the secondary ruptures, like cracks near the rupture from this event. And this de.grd and dn.grd are the deformation grids in the east and north directions derived from a kinematic slip model that's inverted from geodetic data like INSAR and GNSS. So after we have gone through that, let's start plotting. Again, we're going to make some parameters. Say that we want to set up some variables. The DM is actually this file, which is dem.dsam.grd. And we also want the GPS data to be defined. So it's the GPS file. We also want to set the range, but over here, we're gonna set the range based on getting the information from this grid file. There's a really useful command in GMT called grd-info, right? So if we run GMT grd-info on this de.grd, you will see that all the information associated is getting popped out, right? You have the range of this and the increment, how many columns, how many rows, and the basic scale of this grid. So what you can do is that you can append some input with this command that's -i-. This is going to give you the range of this grid, basically this x-min, x-max, and y-min, y-max, because that's what we need for determining the region for plotting, right? And it's going to give you this -r with the 4 parameters. So we're going to use this as the input to define this variable. How we're going to do that. So basically, you give it the quote over here, which is the on your keyboard is the button that's left to your number 1 on top. You're going to quote it and then give it this command. So what this line does is that it's going to get the output from this command and assign it to this RR variable. So next, we're going to do the output. We already specified here, but we're going to define again. Let's say we're going to call it demo, and format being PNG. So here we can change this to $output, and then here $format. So the good way of doing it, like setting a lot of variables at the beginning of this plotting script, is that later on you could just change any of them, and then you can run this script again to create a map for other data. So let's start with plotting a base map. So it's GMT base map. And we're going to use the MapTar projection. Let's give it a size of 6. And we already have this RR variable, so we're just going to call it $RR. Again, we're going to set the -b option. Let's try A1F.5. This time we don't want to plot the grid because in the map there will be other data like DM. If we save it and then run this bash plot map.sh, and it's going to give us a plot. Let's open it. Yeah, demo.png. Do a double column. Okay, now we have a map plot on the right. It's basically just nothing there, as it's just a base map. So the next, we're gonna plot the DM data. So the command we'll be using is called grd image, as we learned yesterday, GMT grd image. And the file, input file will be the $DEM, which is this DEM dsam.grd. And we're gonna illuminate the DEM with -i. And then we're gonna give it a color table called dem.cpt, right? We have that in the directory. But if we run this, yeah, it doesn't look very good. The main reason is because this is too saturated. I mean, you do want snow, but you don't expect this much snow. It looks like Ice Age. So the tool we're going to play with over here is called make CPT. So we're going to make a new color table based on the color table that we have in this directory. Let's do it over here. GMT make CPT. The color table we'll be using will be the dem.cpt in this directory. And we give it a -t, which specifies for the range. You want to scale it. Over here, we're going to do a 0 to, I mean, the zeros are probably somewhere around a couple thousand meters. So let's try 3,000 meters with an increment of 200 meters. Then -d, which means continuous color table and also saturated at maximum number. So in other words, anything that's above this 3,000 will be plotted as the value 3000. So let's call it dem2.cpd or maybe demtemp.cpt. Then over here, we'll change this dem.cpt to the one that's just made. And if we save this and make the new plot, oh, it looks better. But somehow it feels like this gradient's a little bit too strong over here. So we're gonna tweak with this -I option with +n to start to tune the strength of the gradient. We're gonna use a linear case. Let's try exponential this time, -d +ne down 3. If we save this and run the plot map, okay, things are less shaded and looks more reasonable, maybe. Okay, next we're gonna plot the coastlines just as we learned yesterday. Let me move this upward a little bit. So let's try GMT coast. We want to plot the borders. We want to plot all the borders, including the state borders between California and Nevada. We want it to be, let's say, 0.5 pixel with black color and with dashed lines. And we also want to fill the ocean. There are like a tiny bit of ocean over here as well. And we're going to use the -S option with the ocean color, blue, light blue. And we want to plot it at full definition. And also we want the coastline to be plotted with some like maybe black lines. So we can use the -W option with 1 pixel, black. All right, let's run this one more time and see what happens. Let's save this first and then run it again. Oh yeah, like 1 pixel might be too thick. You can't even see this lake over here. Let's try 0.5 or maybe 0.1. Save it. Now we can see the lake. Cool. After that, we'll be using the command called grd vector to plot the vector deformation field. So over here, and we're going to plot it on top of this whole thing. GMT grd vector. Let's give the input file called de.grd and dn.grd. Over here, there will be a -S option to sort of tell you the scale that's going to get used. Over here, we're going to give it like 50. Because if you think about the deformation we just saw, actually the range is like largely from -100 to 100. And since we're using the 6 as a size, we want the largest vector probably being like somewhere less than 2. So we're giving it this 50 over here. And we want the -I option, which is just 0.1 increment. So every 0.1 degree is gonna give a new input vector. And the width to be, we want it to be very thin because we'll be plotting a lot of vectors, 0.1 pixel. And for the vector attributes of grd vector, you'll be using the -Q option. Well, here we're going to give it a 10 pixel size at the end with a, we're just going to do a plain arrow this time. Oh, it's +EA, sorry. And if we save this and run it one more time, yeah, it says no unit specified in -S, but it's okay. Now you have this vectors plotted, like you can sort of see this lateral motion, like the rupture this way and that way. Also in this grd vector command, there is this new auto labeling option, which is called -L. And for example, I want to give it, because the scaling that you're giving here is about a 50. I'm going to try this default 50 millimeter. And if you run this one more time, you have this automatic label on top. But if you want to plot, for example, a much smaller like label, I don't want this to be 50, I want this to be 20 or 30 maybe, you can actually change it over here. But you also need to give it a +S option to scale this, because that's basically only like 0.6 of the 50 millimeter. So you're going to use a 0.6 over here. If you save it and then do it one more time, then this auto label becomes 30 millimeter. Okay, what's next? Next, we're going to plot the faults on top of this. And the command we'll be using is called GMT plot. The file is new faults.gmt. But before we do this, let's take a look inside what's in this data. And you'll find that this is basically like a bunch of segments that records where the rupture starts and ends and how it curves in space. They are separated with this -L in the data. So GMT knows like there are like multiple segments that you'll be plotting. And we want it to be, for example, 0.5 pixel wide with, I don't know, maybe orange colors. And if we save this and run this bash plot again, oh, you see some like new fault ruptures in it. All right, next we'll be plotting the GNSS data. But before we really do that, we want to plot the GNSS stations first. We're going to use this plot command again, and then $GPS. We're going to plot them in triangles with maybe 0.15 size. And the outline will be in 0.1 pixel with black colors. And for the fill, we're going to give it maybe in green. GREEN. If we save this, I run it. Okay, all the GNSS stations shows up on this map. Next, we're going to plot the vectors, GMT willow and $GPS. We're going to use the same scale that's specified here, -S, because this is the length scale. Let me try to put an L over here so that it doesn't warn me anymore. -S 0.02. And we want to plot, because uncertainty with assign it's pretty small. Let's do a 99 so that you guys can see the circles, and font size being 10. And we're going to use the -A option, 10 pixel size arrowhead at the end with a fancy arrow. And then we're going to give it a width of 0.1 pixel. And we're going to use blue colors maybe. And for the fill, we want to give it a black colors. And if we save this and unrecognized, oh, I forgot to give it a -SE. Do this one more time. Ooh, what happened? Yeah, I don't know what happened, but oh yeah, but just -L. Leave that for the moment. Essentially, you could do the same thing as this scale over here, which is -I.02. So they are the same. Now that we have finished plotting all the vectors, but what if we want to plot something else? For example, we want to plot the amplitude of the deformation on top of this map. While the deformation is being shaded with the topographic information over here, And then you use these vectors to denote the deformation direction. So how are we going to do that? So the way you do it is actually, you could create a new grid using the GMT functions over here. For example, so GMT is actually a pretty powerful tool that can not only just do plotting, but it can calculate grids as well. So the command we'll be using is called GMT GRD map. So the way we do it that because we have the eastward deformation, north deformation, we can combine these two together to get the amplitude of deformation. And this GRD mass also uses a format called the reverse polish like approach or something. You guys can Google that. It's a pretty fun way of writing things. So we're going to give the de.grd, de.grd. We're going to multiply these two together. We're going to do the same thing for the north component. And then after these two squares of E and N, we're going to add them together and then do a square root of it. And the output file, we're going to just call it like d.grd or something. So now we have this amplitude image. Let me make this a little bit wider. So now we have this deformation grid. Then how are we going to plot it? We're going to need a new color table, right? So we'll be making a new color table. We'll be using, for example, jet. This time we're going to do a sort of red to green. We're just going to use half of the color bar. So we'll be using -t option from negative. We want it to be a little bit saturated so that you can sort of see the impact of the earthquake. Let's try 30, -30, 230 with a 5 increment -c -d into d.cpt. All right, but we do want to plot this before we do any other overlays like the coastline and the vectors. We want it to be on the background, so we had to select the position to implement it. So we're going to replace this GRD image command of the DEM with the deformation. So we're going to hashtag this to comment it out, and GMT GRD image d.grd minus C. We're going to use the e.cpt file. What else? I think that's pretty much it. And if we save it and run this one more time, oh, you see that they have the deformation field in the background, right? Okay, next we're gonna shade this image so that we can see some of the topographic information. And the command we'll be using is called GMT GRD gradient. This is similar as the -i option where you are plotting using the GRD image, but this is more flexible that you can use a lot of parameters to control it. But before we do that, since we're going to use the shading of this deformation grid, you have to sample your topography grid to the deformation grid first, so that those two grids are matching up. So we'll be doing a GMT GRD sample, the $DEM and -r de.grd. So this is actually sampling the DEM to the size and sampling of this DE grid. And the output grid will be, let's call it a DEM temp.grd. Now we have this DEM temp. We're going to work the gradient on it. Again, we're going to use the -n option to specify the, how to say, which direction you are essentially, not which direction, like how large of a gradient you're going to give it. For the moment, let's try the NE 0.3. And you also need the -a option, which is like which direction you'll be doing this gradient. The default is -45, so we're going to just use -45 degrees for the moment. And the output grid will be DEM temp gradient.grd. If you save this, and then while you are plotting this GRD image, we give it a -I option, and then give it this file name. So it's going to use this file as an illumination for the plotting. If you save this and run it one more time, now you can see that the the topography information are actually shading the image, which is pretty cool. Okay, I think that's pretty much everything for plotting vectors. If you go to that GitHub page that we started, you see that there are more things that you can add to this map, like the focal mechanism, the epicenters, and maybe you can find like data for other earthquakes to play with. So feel free to experiment on that. And I think I only missed one thing from this plot vec, which is to how do you like color these vectors. So I'm gonna try that, sort of like show you guys how to do it on this plot vec script again. Let's try to open that PNG file, do a double colon. So actually, GMT allows you to sort of give a color table to color these vectors. I didn't like sort of go through that at the beginning because that's sort of like a new feature I think Paul just implemented. And we're going to expand the data a little bit. Let's try it without this double couple. Let's comment it out. And we don't want just half of it. And duplicate these lines like 3 times so that we have 3 vectors to play with. Now let's change this start and end. Let's start from 0.5 for this one. And also we want the deformation to be 0.5 and 0.5. Then we get a slightly smaller uncertainty. The other one, I'm going to start from -0.5 and with large amplitude. So you see like 3 vectors in this plot. Give the larger uncertainty. Let's just give it some strange numbers. Let's do this. Bash plot vec.sh. Oh yeah, forgot to comment this line. And you also need this part to be double redirect because that's like creating a file and this is appending to that file. So you have 3 like lines of data in the file. We run that one more time, you see like 3 vectors parallel to each other. We do want the error bars to show up. Give it a 0.99. Oh, that's too big. 6.5 is good. All right. So how are we gonna color these? Like, if you want to give it a color table, you can actually, but you need to make a new color table first. Let's do the GMT make CPT one more time. I'm gonna use rainbow with -T0 to 2.5, like 0.5 maybe. B minus D into vec.cpt. Then what you can do is that you sort of give this a -C option with the vec.cpt. If you save this script, run this one more time, give it, seems nothing's getting changed, but that's because you have this +G option that's overriding this coloring option. So we had to remove this part in order to let it work. Run it one more time, you see that these arrows are having different colors now. And we're gonna make a color bar over here, GMT color bar -C vec.cpt, and the -dx going to start with 0.1, 0.1, plus W. Let's do 1.5 over 0.1 and save it. Now you have a color bar that tells you like how large are their values. The thing is that if you want to, for example, not just color the arrow, but on the other hand, you want to color these lines as well, then you have to modify this minus W option. You have to give it a plus C. Then it's going to color the lines as well. It's using this color table. If we save it here and then run the bash again, they're going to be with these colors. Another thing you can do is that if you are really bugged by this outline, you don't want it to have a black outline or any color outline, you can essentially just give it a 0. Or no, you can just essentially give it a no input over here. So it's not going to plot anything. Now things are becoming a pure color. Okay, that's pretty much everything I want to show here. Feel free to play with the data. Thanks.